The world is betting on renewable energy. But the more solar and wind we add, the more unstable the grid becomes. We're running into a wall, and the only technology powerful enough to break through doesn't generate energy at all. It stores it. We stand at the precipice of a clean energy revolution, an era powered by the sun and the wind, limitless, carbon-free energy that promises to heal our planet and secure our future. It's a beautiful vision. But this vision is haunted by a fundamental paradox, a critical flaw that threatens to derail our progress before it truly begins. The sun doesn't always shine, and the wind doesn't always blow. This simple truth, known as intermittency, is the single greatest challenge of the 21st century power grid. Our sources of clean energy operate on their own schedule, not ours. And this mismatch between when power is made and when it's needed creates a profound and dangerous instability. To understand this problem, we have to look at the rhythm of our daily lives. Every day, our collective energy use follows a predictable pattern, a load curve. It starts low in the early morning hours while we sleep. Then, as a city wakes up, as we turn on lights, brew coffee, and start our commutes, demand begins a steep climb. It often dips slightly around midday when commercial buildings are running efficiently and many people are at work. But the real challenge comes in the evening. As the sun sets, we return home. We switch on the lights, cook dinner, watch television, and charge our devices. This creates a second, much larger surge in demand, the evening peak, which is the moment of maximum strain on the grid. Now, let's overlay the generation profile of our most abundant renewable source, solar power. Solar generation, logically, peaks at high noon when the sun is most intense. This creates a massive surplus of energy right in the middle of the day when demand is relatively low. But as the sun begins to set, solar output plummets, precisely as evening demand begins its rapid ascent. The resulting graph, first identified by grid operators in California, is so distinctive it was given a name: the duck curve. The belly of the duck represents the midday oversupply of solar. The neck represents the incredibly steep, dangerous ramp-up in demand that the grid must meet as the sun disappears. Every evening, grid operators face the monumental task of replacing gigawatts of solar power with other sources in just a few short hours. And as we add more solar to the grid, the duck's belly gets deeper and its neck gets steeper, making this daily challenge ever more perilous. Wind power presents a similar, if less predictable, problem. It can blow fiercely at night when demand is low, or fall completely silent during the day. One of the most critical scenarios is a summer heat wave. A stagnant, high-pressure weather system can settle over a region for days, bringing scorching temperatures and, crucially, very little. This is precisely when demand for air conditioning skyrockets, pushing the grid to its absolute limit. At the very moment we need the most power, wind generation can collapse. So, what happens when the sun sets and the wind dies? How do we keep the lights on? The answer, for now, is a fleet of archaic fossil-fueled power plants held in reserve for just these moments. They are called peaker plants. These are typically natural gas or oil-fired turbines designed to fire up quickly and fill the gap left by renewables. They are the grid's brute force solution. But this solution comes at a staggering cost. Peaker plants are incredibly expensive to run, often charging many times the normal price for electricity. They are also the least efficient and most polluting form of generation. They sit idle most of the time, only to roar to life and emit significant amounts of carbon dioxide and other pollutants to save us from blackouts. They are a dirty, costly, and inefficient crutch, undermining the very purpose of our clean energy transition. The problem is compounded by the very architecture of our electrical system. Our power grid is a 20th century marvel of engineering, designed for a world where energy flowed in one direction. Giant, centralized power stations, coal, gas, nuclear, produced a constant, predictable stream of electricity. This power was pushed out across a vast network of transmission and distribution lines to passive consumers like homes and factories. The system was built for predictability and central control. But that world no longer exists. Today's grid is a chaotic, decentralized ecosystem. Millions of homes have become miniature power plants with rooftop solar. Wind farms inject huge, fluctuating amounts of power. And a growing fleet of electric vehicles creates massive, unpredictable spikes in demand whenever they plug in. Power no longer flows in one direction. It zips back and forth, creating congestion and stress on lines and transformers never designed for such a complex dance. The system is overwhelmed. It's being pushed to the breaking point daily. This leads us to a crucial realization. The challenge of the clean energy transition is not a lack of generation. On a sunny, windy day, we often produce more clean electricity than we can possibly use. The system is literally overflowing with power. We don't have a generation problem. We have a timing problem, a grid problem. We have a storage problem. To understand why our modern power grids are becoming so fragile, we must first grasp their most fundamental, non-negotiable rule. Electricity must be consumed the exact moment it's generated. For over a century, this principle has been the bedrock of grid management. There was never a way to store vast amounts of energy efficiently, so the entire system was engineered around a delicate, real-time balancing act. Think of the grid not as a reservoir, but as a tightly synchronized dance. The music for this dance is a constant, unwavering electrical frequency, 60 Hz in North America, 50 Hz in most of the world. This frequency is the grid's heartbeat. When supply perfectly matches demand, the heart beats steadily. Every appliance you turn on, every factory that powers up, adds a little more demand. In response, grid operators must instantly command a power plant somewhere to generate a little more supply. It's a system of perfect, instantaneous equilibrium. The secret to maintaining this stability has always been inertia. Traditional power plants, coal, gas, nuclear, use massive spinning turbines, some weighing hundreds of tons. This immense rotating mass acts like a powerful flywheel. It stores kinetic energy, providing a physical buffer that resists changes in frequency. If a large factory suddenly goes offline, reducing demand, the grid's frequency tries to rise. The inertia of these giant turbines slows that rise, giving operators precious seconds to reduce generation and restore balance. Conversely, if a power plant unexpectedly trips offline, the turbine's momentum continues to feed a tiny bit of energy into the grid, slowing the frequency's fall. This physical inertia is the grid's shock absorber. It's what has kept the lights on reliably for decades. But intermittency breaks this rule. Solar and wind power are fundamentally different. They don't have massive spinning turbines. Instead, they connect to the grid through power electronics, inverters that convert direct current into alternating current. While essential, these inverters provide virtually no physical inertia. As we replace the old heavy turbines with silent, static solar panels and inverter-based wind farms, we are systematically removing the grid's natural shock absorbers. The system becomes brittle. A sudden cloud cover over a massive solar farm or an unexpected drop in wind speed can cause a supply drop that is far faster and more severe than a traditional plant tripping offline. Without the buffer of inertia, the grid's frequency can plummet in milliseconds, not seconds. This leads to a cascade of secondary problems. First, ramping. As the sun sets, solar generation collapses. Just as people are returning home from work, turning on lights and cooking dinner, causing demand to spike. The grid needs to ramp up an enormous amount of power in a very short time. This task falls to fast-acting, but expensive and polluting, natural gas peaker plants. Then there's congestion. On a sunny, windy afternoon, a region might produce more renewable energy than its transmission lines can carry away, creating an electrical traffic jam. The grid operator's only solution is a wasteful one: curtailment. They are forced to order wind and solar farms to shut down, deliberately throwing away clean, free energy simply because the grid cannot handle it. These aren't theoretical problems. They are happening now, all over the world. In Germany, massive midday solar generation sometimes exceeds demand so greatly that electricity prices turn negative. Producers have to pay consumers to take their power. In California, the infamous duck curve leads to a frantic evening ramp, straining the grid to its limits and contributing to rolling blackouts when supply can't keep up. Australia, with its high renewable penetration and long, thin grid, has faced major instability events where a lack of inertia nearly caused catastrophic statewide collapses. Each case is a warning sign. Without a buffer to absorb the shocks of intermittency and a brain to manage these complex new dynamics, renewable heavy grids behave like overloaded computers running critical software with no memory. One imbalance, one unexpected event, can trigger protective relays to trip, isolating sections of the grid to prevent damage. But this can create a domino effect, where the loss of one section overloads the next, leading to a cascading failure where entire regions collapse into darkness. The very technology meant to save our planet is, paradoxically, threatening the stability of the system that delivers its power. The old rules no longer apply, and the old system is breaking. We need a new component. We need a brain to manage the chaos. We need a buffer to replace the lost inertia. We need storage. The solution to the grid's greatest challenge, the intermittency of renewables, is not a new form of generation. It's a new form of control, a revolution in storage. Battery energy storage systems, BESS, have changed everything. And to be clear, this isn't about the battery in your phone or your laptop. These are monumental, gigawatt-scale machines, engineered to stabilize the energy supply of entire nations. They are the missing piece of the clean energy puzzle, the silent partner to wind and solar, transforming them from intermittent sources into a firm, reliable, 24/7 power supply. For decades, the grid operated on a simple principle: generate power precisely when it's needed. But BESS shatters that paradigm. It allows us to capture energy when it's abundant and cheap, in the middle of a sunny day or a windy night, and deploy it hours later, when the sun is set and demand is peaking. This simple act of time-shifting energy is rewriting the rules of power economics and engineering. Let's delve into the core technologies that make this revolution possible. 1. Lithium-ion, the reigning champion. At the forefront of this charge is the technology that untethered our digital lives, lithium-ion, but scaled to an industrial epic. The reasons for its dominance are clear. It's fast, flexible, and increasingly affordable. Lithium-ion batteries boast incredible energy density and near instantaneous response times measured in milliseconds. This speed is critical for a service known as frequency regulation, the constant, delicate balancing act of matching power supply to demand. When a large power plant unexpectedly trips offline or a cloud bank covers a solar farm, the grid's frequency can dangerously deviate. A lithium-ion BESS can inject or absorb massive amounts of power almost instantly, arresting that deviation far faster than a gas-fired peaker plant could even begin to spin up. But not all lithium-ion is created equal. The industry is rapidly coalescing around a specific chemistry, lithium iron phosphate, or LFP. Early grid batteries often used nickel manganese cobalt, or NMC, the same chemistry popular in electric vehicles due to its high energy density. However, NMC chemistry relies on cobalt, a mineral plagued by price volatility and severe ethical concerns in its supply chain. It also carries a higher risk of thermal runaway. LFP, by contrast, is cobalt-free. It uses abundant and inexpensive iron and phosphate. While slightly less energy dense, it is fundamentally more stable, offering a superior safety profile and a significantly longer cycle life, often double or triple that of NMC. For a stationary asset designed to operate for 20 years, that longevity and safety are paramount. This is why LFP has become the de facto standard for modern grid-scale storage, deployed in the world's largest projects across California, Australia, and China. 1. Flow batteries, the marathon runner. While lithium-ion excels at rapid response, a different architecture is purpose-built for endurance, the flow battery. The most mature of these is the vanadium redox flow battery, or VRFB. Unlike conventional batteries where energy is stored in the electrodes, a flow battery stores energy in two large, external tanks of liquid electrolyte. To charge or discharge, these liquids are simply pumped through a central stack of electrochemical cells. This elegant design decouples energy capacity from power output. Need more power? Make the cell stack bigger. Need more energy duration? Just install larger tanks and fill them with more electrolyte. This makes them exceptionally well suited for long-duration storage, designed to discharge continuously for 8, 12, or even 24 hours. Their key advantage is durability. The vanadium electrolyte doesn't degrade like the solid electrodes in lithium-ion batteries, giving them a near-infinite cycle life. The same liquid can be charged and discharged for decades. This makes them a perfect candidate for solar shifting, absorbing a full day's worth of solar energy and releasing it throughout the night, ensuring a stable, continuous supply. While still more expensive up front than lithium-ion for short-duration applications, their exceptional lifespan and scalability for long-duration needs are making them an increasingly vital part of the storage portfolio, especially as grids aim for higher and higher penetrations of renewable energy. 1. Emerging chemistries, the challengers. The innovation doesn't stop there. A new contender, sodium-ion, is rapidly moving from the lab to commercial scale. Built on the same principles as lithium-ion, it replaces lithium with sodium, one of the most abundant and inexpensive elements on Earth, found in common salt. This eliminates reliance on the strained lithium supply chain entirely. While current sodium-ion designs have lower energy density, they offer excellent safety, a wide operating temperature range, and the promise of dramatically lower costs. They are a drop-in replacement for LFP in many stationary applications, and major manufacturers are already building gigafactories to produce them. Further on the horizon lies the holy grail, solid-state storage. By replacing the liquid electrolyte with a solid material, these batteries promise a step change in energy density and safety, virtually eliminating fire risk. While still in development, with research hubs in Japan and the EU leading the charge, solid-state technology could one day enable even more compact and powerful storage systems. 1. The digital brain, management, and safety. A BESS is far more than just a collection of cells. It's a highly sophisticated system governed by layers of intelligent software. At the most fundamental level is the Battery Management System, or BMS. This is the battery's guardian, a dedicated computer that monitors every single cell, tracking its voltage, temperature, and state of charge. The BMS ensures the battery operates within its safe limits, protecting it from overcharging or overheating. It performs cell balancing to maximize performance and lifespan, and in the event of a fault, it can instantly isolate a problematic module to prevent a cascading failure. The BMS is the foundation of battery safety. Overseeing the entire site is the Energy Management System, or EMS. This is the system's brain, making the high-level economic decisions. The EMS communicates with the grid operator, monitoring market prices for electricity. It decides when to charge, when prices are low or negative, and when to discharge to sell power for a profit. In more advanced networks, this is handled by a DERMS, a Distributed Energy Resource Management System. This AI-powered platform acts as a digital twin of the grid, using neural networks and predictive algorithms to forecast energy demand, weather patterns, and market fluctuations. It optimizes not just one battery, but a whole fleet of resources, solar, wind, and storage, orchestrating them in perfect harmony to maximize both grid stability and financial returns. This is neural grid optimization, enabling predictive charging and instantaneous response on a system-wide scale. 1. Renewable hybridization, the ultimate synergy. When these technologies are brought together, the true transformation occurs. This is renewable hybridization. By co-locating a BESS directly with a solar or wind farm, we create a single, dispatchable asset. The battery absorbs energy during peak production, smoothing out the variable output and preventing curtailment. The wasteful practice of shutting down turbines or panels when the grid can't handle their power. The result is a hybrid power plant that can deliver clean, reliable 24/7 power, behaving on the grid just like a conventional power station, but with zero emissions and far greater flexibility. The proof is already on the grid. In South Australia, the Hornsdale Power Reserve, famously built in under 100 days, became a landmark case study. Shortly after its commissioning, a major coal plant failed. Before the legacy fossil fuel backup generators could even begin to respond, Hornsdale injected 100 megawatts into the grid, stabilizing the frequency in a fraction of a second. In its first 2 years alone, this single battery saved consumers more than $150 million in grid stabilization costs by absorbing instability faster and more cheaply than any fossil fuel plant could ever react. Ultimately, the viability of this revolution comes down to economics and sustainability. The key metric is the levelized cost of storage, or LCOS, which calculates the total cost to store and discharge a unit of energy over the battery's lifetime. Thanks to plummeting manufacturing costs, LFP lithium-ion now offers the lowest LCOS for most applications today. But as flow and sodium-ion technologies scale up, they will provide competitive alternatives tailored for different needs. And the story doesn't end when the battery's life is over. A robust recycling industry is emerging, capable of recovering over 95% of critical materials like lithium, cobalt, and nickel. This creates a circular economy, turning a potential waste stream into a valuable resource for building the next generation of batteries. BESS is no longer a niche technology or a form of backup. It is the enabling infrastructure for a 100% renewable grid. It provides speed, stability, and intelligence. It is the new backbone of our energy future. The global battery boom is unlocking 3 transformations. 1. Climate impact. BESS removes the need for fossil peaker plants. Millions of tons of emissions cut instantly. 2. Economic impact. Energy costs drop. Blackouts become rare. Energy companies shift to service models. 3. Resilience. Microgrids keep hospitals, schools, airports, and entire towns powered even when the main grid collapses. What does a fully stored world look like? Homes with rooftop solar, plus local batteries, EVs acting as mobile grid support, AI predicting power demand, minute by minute, digital twin cities optimizing energy flow, zero-emission power available 24/7. Battery chemistry will evolve. Sodium, zinc, vanadium, organic liquid, cheaper, safer, abundant. The next century will be electrified, and batteries will be its foundation. Humanity doesn't lack energy. The sun sends more power in 1 hour than we use in a year. Our challenge is capturing it and saving it for when we need it. Battery energy storage systems are the key that unlock a renewable world. Stable grids, clean cities, a carbon-zero planet. What do you think is the biggest challenge for global battery adoption? Cost, materials, or public understanding? Share your thoughts below.